I wrote this, or I copied this from the textbook, and this is just a general version of the chain rule that gives us a holistic formula for any kind of derivative that you might have to come up with using the chain rule. But the only thing that we should worry about is that if the number of functions you have for the most inner function, if you just have one variable in that, then these partials over here wouldn't be partials. They would just be straight D's instead of regular D. And so that's similar to our first example that we did yesterday. Okay. Today we're going to take a look at this as our first example, where we're finding the derivative of the function. Use a table of values to calculate GU evaluated as 0, 0, and GV evaluated 0, 0. Okay? So this is saying that G is a function of U and V, and then U is that first component, and then V is the second component. I'm sorry, not U, that's F, X, and Y. So this is where the notation can get a little bit screwy, but we just have to kind of look through the names of these functions and what they mean. So like the top function, we can call it G or F. Doesn't really matter, but we know that that's a function of X and Y. So regardless of what we call it, it's a function of X and Y, although they say F is a function of X and Y. And G overall is a function of U and V at the end. Do you guys prefer the separate U's and V's, or the same U's and V's and then just connect it separate? So whether you call this F or G, it doesn't really matter. But in the end, we'll see that G is going to be a function of U and V, and then F originally is a function of X and Y. So they kind of mush this together. So if we can collect our different parts here, we can see that X is equal to, well, let's say X as a function of U and V is equal to e to the U sine V. Is that a plus sine V? And then Y as a function of U and V is equal to e to the U plus cosine of V. So that'll help us find our different values in different components. So actually, I should have continued and finished up this diagram. We have G, or F. Let's call it F. And then X is a function of U. We'll get a partial of X with respect to U, and then the partial of X with respect to V. And then F as a function of Y, we'll get the partial of F with respect to Y, and then the partial of Y with respect to U, partial of Y with respect to V. So if we create our partial that we need, we want G of U at 0, 0. So this is where we have to really be careful about what these variables are. These variables look like they should be variables of u and v, because they're saying g is a function of u and v. So we'll keep that in mind. According to our diagram here, we want to get to u, and there's two paths to get there. We're going to take this path going through x, so that's the partial of f with respect to x times the partial of x with respect to u plus the partial of f with respect to y times the partial of y with respect to u. Okay. So we need to identify some of these values. So we need to figure out what these dx du's are and dy du's. So let's figure that out first, and then let's see where we need to go from there. So x, I'm going to switch notations. X sub u, that's the partial of x with respect to u. So the derivative with respect to u is e to the u. The v is gone. Okay. And we want this evaluated at when u is equal to 0 and v is equal to 0. So x sub u evaluated at 0, 0, 0 for u and 0 for v. We're going to get e to the 0, which is going to be 1. Okay. Oh, sorry, we're going to be interested in one more thing too. We'll talk about that in a minute. But let's finish taking the derivatives here. U, or y, of u is equal to e to the u again, and y of u evaluated at 0, 0 is going to give us e to the 0 again, which is 1. So it looks like we're going to have 1 for these values here. Okay? Now we need to figure out what f, the partial of f with respect to x is evaluated. But see, the partial of f with respect to x, we're going to take intermediate steps here. So I'm going to write down the partial of f with respect to x. That's the same thing as f sub x, right? But this is evaluated when f is a function of x and y. So we can put x and y here, but we have to make sure we put the x and y values when u and v are equal to 0. So again, this is u and v. And so what we need to do is we need to figure out what x is equal to when u and v are both equal to 0. So I'll do that over here. X of 0, 0. And this is my x function. X is equal to e to the 0 plus sine 0, which is equal to 1. 1 plus 0 is 1. And then we have y at 0, 0. This y value over here is equal to e to the 0 plus cosine of 0. Cosine of 0 is 1, so I have 1 plus 1. That's equal to 2. So what we really need from this table is f sub x of x at 0, 0 is 1, and y of 0, 0 is 2. And according to this, fx evaluated at 1, 2 is equal to 2. So from the table, we have 2 for that expression here, the partial of f with respect to x. So let's go ahead and put that here. So the last bit of information is the df dy, and we're going to walk through the same process, except we already know what happens when you put 0, 0 in for u and v into the x and y functions. So we know that this is going to be 1 from the work we just did, and this is going to be 2 from the work we just did. So really, we're looking for f sub y evaluated at 1, 2. This time we look at this number. Get this from the table again. And so we get to put that in for our 5. All right, so it looks like it's 2 plus 5 is 7, so this whole thing is equal to 7. Okay? All right, so what was the difficult part here? What do you think? Keeping track of all the steps, right? I think the very first thing to make sure you do is to draw the diagram. It seemed like it was straightforward yesterday, but now when we're looking at the way they write the functions, it gets a little trickier, so you just have to be careful with that. So the diagram, from the diagram, come up with your formula. And then from your formula, you have to figure out what pieces you need. And here the variables got a little tricky, but if you just try to go back to your diagram and understand what is a function of what, and then those variables should come out a little bit clearer. So this is only one of them. There's another one that's GV of 0, 0, but we're not going to do that. You guys can try to figure that out. You set up the same sort of formula, and then you find the components of what's needed. You'll probably still have to use the 1, 2 things. Except the only different thing that you'll have is dy du, and the dy du will will ask you to take the derivative of x and y with respect to u, or v, I'm sorry. It's going to be dx dv and then dy dv. And then so you need to take the derivative with respect to v for both of these functions, and then these things will probably change. Okay. All right. Let's talk about implicit functions now. You know what implicit functions are? Do you remember what they are? X and y, and then the implicit differentiation is when you do derivatives with implicit functions. So here's an example of implicit function, but before we do that, let's do a different implicit function. So back in Calc 1 or 2, I think it's Calculus 1, we dealt with graphs, and I wouldn't really call this a function. I would call this like a relationship between x and y. Do you guys remember looking at a graph that looked like this? This is some special graph or something. I think it's called the witch. I don't know. Maybe I'm just making it up. Let's see if I'm making it up. No. Maybe it's not the witch. Yeah, it's close. Well, any case, it's something. So this is, you know, the vertical line test business doesn't work here, so it's clearly not a function. But they say it's an implicit function because we might not be interested in looking at the whole thing, but we may be interested in just looking at a piece of this graph, and then doing some analysis, some calculus on the piece of this graph. So if we take a piece of this graph, you know, it's hard to solve for y here. There's addition. That's usually what we would like to do, is solve for y. And then when we solve for y, then you have y is equal to something with an x in it. But if you try to solve for y here, it's pretty impossible. And if you do manage to solve for y, then you're only going to get pieces of the graph as a function. So if we, for example, take a look at this graph, if we take a look at this graph and just take a piece of it, let's say maybe this piece right here, then we can say that that would pass the vertical line test, and that would be a function. So this possibly would be y is equal to some function of x. If we were somehow be able to solve for y in this thing, we'll get a piece of that piece of a graph. And so implicit functions takes a look at relations between variables, x and y, and then asks you to be able to try to find derivatives of these things, so that we can do things like find the rate of change at this point or something. Find the slope of the tangent line or something. Okay? So if you remember what you did with implicit differentiation, I think, do you remember what you did? So we say d dx, we take the derivative with respect to x of this thing. And then we take the derivative of this with respect to x, we say it's 3x squared Really, we multiply by dx over dx. It's like the derivative of x with respect to x. So it's like a chain rule that we're applying. Oh, now this is going to be hard. It's not that hard, but it's a product. So I'm going to keep the negative 3 outside and just focus on the xy. So derivative of the first times the second plus the first times the derivative of the second. So this is the dy dx that comes out that we'll need to solve for. And then you take the derivative of this with respect to x, 3y squared dy dx. And then this is equal to 0. So you remember doing something like that? Except instead of a dx dx, you just probably didn't even think about it and called it 1. And sometimes you just say dy dx instead of saying dy dx, you just call it y prime or something. Anyways, that's the implicit differentiation that you did. And then if you want, you can solve for dy dx here, because that's eventually what you'll need to do. But instead of solving for dy dx, let's pause for a moment and think about partial derivatives, because that's what we're dealing with. We're doing partial derivatives, right? So let's think about partial derivatives and see how this works with partial derivatives. And imagine ourselves taking the derivative with respect to x. So if we do this slightly differently, instead of doing a straight d dx, let's take a look at partial with respect to x. And if we take the partial derivative with respect to x here, we're going to see that, let's call this a function. Let's rewrite our function here. Let's call it f of x comma y is equal to x cubed minus 3xy plus y cubed. And this is equal to 0, so let's not worry about the 0 part, and let's just treat this as if it was a function. And what we could do is we can do this partial derivative that I was just talking about. Let's say partial with respect to x, partial of f with respect to x. And then what do we do? Let's take the derivative with respect to x. This is 3x squared minus, this is just negative 3y, right? And then the y cubed is gone. And then let's take the partial of this with respect to y. This is going to be negative 3x plus 3y squared. Now, what I want you to do is take a look at the old implicit differentiation, the way we did this with respect to the straight d with respect to x, and see if you can match the different components that we have there. Can you see it? No? Yeah? Let's see. Let's do some matching up here. So it looks like the df dx is getting multiplied by dx dx. And then if we remember to bring in this negative 3 over here. This is a negative 3x, and then this is a 3y squared, and that's being multiplied by dy dx. So I guess what I'm trying to say here is that this thing can eventually be taken the derivative with respect to x as an implicit differentiation problem, d dx. Now the straight d is kind of dangerous in doing this with a straight d, but we're assuming that y is a function of x. I don't know if I really want to do that. Let's not do that. And let's just think about this as this expression over here is really the partial of f with respect to x that's being multiplied by dx dx, or 1, and then we're adding the partial of f with respect to y and multiplying that by dy dx. And then remembering that this is equal to a constant, so let's just throw 0 on the other side, because the derivative of 0, or any constant for that matter, is equal to 0. And then if we're interested in solving for dy dx, we can just use this formula to solve for dy dx. So dy dx is equal to, let's see, oh, dx dx is equal to 1. We could have replaced it with 1 in these previous examples that we've done. So it looks like I just need to, what do I need to do? Bring the df dx over to the other side, df dx, and that gives me a negative df dx, and then I need to divide out by df dy. And so this is my implicit differentiation formula from Calculus 1. So if we had a relation between x and y, and we're looking at a two-dimensional relation graph that may or may not be a function, we can do implicit differentiation by bringing everything over to one side, pretending that we have a function of x and y that's equal to 0, and then we can simply use this formula to get our implicit differentiation problem. Okay? All right, so that looked interesting. And then if you mistakenly pretend like you're doing algebra, and then you can look at this, and this is like dy dx if you simplify it, right? The df is a fraction. You can work things out to make it look like dy dx. But we don't want to do that because these partial derivatives work differently when we add more variables to it. So, but this is like back with dy dx, a function of one variable kind of business. But when we throw in a third variable, it's going to look a little bit different. So this is an example of an implicit function problem in 2 dimensions where we have x and y. Now let's take a look at an example of an implicit function problem in 3 dimensions where we introduce the z component, the z variable. And for this, let's talk about this in general terms, and just to make it slightly different from the f of x, y functions that we've been dealing with, I'm going to call it capital F of x, y, z. Equal to 0. And say that this can implicitly possibly, if you can somehow solve for z, we can somehow solve for z, we can write it as z is equal to f of x, y. And I'm using little f purposely different from capital F to say that little f is a function of 2 variables, capital F is a function of 3 variables. And I say implicitly because sometimes we can't actually solve for it. You know, there's some easy ones. If you just have z, let's throw in a couple of examples here. X squared plus y squared plus z squared is equal to 4. Let's say is a sphere, radius 2. If you look at it together like this with z being squared, then we can solve for z and get plus and minus the square root of something that will give us a top and the bottom half of the sphere. So that's easy to understand, I think. So in this case, we can have two separate functions that describe the whole surface. But there are other examples here where I have, for example, e to the z is equal to x times y times z. And that you can just say, well, if I solve for z somehow, I might be able to get some piece of the function, but it looks like it's going to be too difficult to solve for z. So we can say that this can be implicitly done if I have the surface and say I want to find the tangent plane to the surface somewhere. I can just pretend that I can write the function z as a function of x and y implicitly or explicitly, but I'm not going to be able to solve for it explicitly, so I have to work with this as an implicit function. Okay, so the question is, we're going to work on one or two of these examples, but let's take a step back and ask ourselves, we want partial derivatives with respect to x and with respect to y for various reasons. So let's say, how do I find the partial derivative of z with respect to x, for example? Well, if we could solve for z, then we'd just solve for z and take the partials, and that's not a bad idea. But if we're going to do this with respect to x, what we have to do is we have to take the derivative of this thing with respect to x and see what we get. And so for this, the diagram isn't necessarily recommended, and we just have to try to remember some formulas. But if you can, because the diagram gets a little confusing here, but if you can imagine how the diagram would look like, maybe it might work. So let's see how this is going to work. So f looks like it's a function of x, y, and z. And what we're doing is we're pretending that we can explicitly write this as a function of x and y. We're pretending that we can write this explicitly as a function of x and y, even though we can't. So we're going to assume that each of these are functions of x and y. Now, our z, this is our dream, right? To write z as a function of x and y. But because z is kind of like the same level of variable as x and y, this whole diagram looks all messed up already. I kind of want to erase it now. Oh, let's work with it and pretend that we're following through this diagram. So we have the partial of f with respect to x and the partial of x with respect to x. The partial of f with respect to y, and then the partial of y with respect to x. Partial of f, this is all capital F, with respect to z, the partial of z with respect to x. So those are my different components that I have to deal with. So according to my formula, I have the partial of f with respect to x times the partial of x with respect to x plus the partial of f with respect to y times the partial of y with respect to x plus the partial of f with respect to z, partial of z with respect to x. That's the derivative of this thing, and it's supposed to be equal to 0, so let's say that that's equal to 0. So what we have here is, this is what we're looking for, dz dx. So if we just bring everything to the other side, let's see what happens when we bring everything to the other side. dz dx is equal to, so this thing has a coefficient that I'm going to divide by. Let me do that first, which is normally what we do last. So df dz, and then now let's bring everything to the other side, which will give you negatives. So negative df dx times dx dx minus df dy times dy dx. Right? So the dx dx looks like it's just going to be 0. I wonder what the dy dx is supposed to be. What is that supposed to be? I can't remember. Wow. Let me look at the book. Oh, yeah, sorry, 0. Guess we should have worked that out, huh? The dx dx is what? It's 1. And if we're treating y as a variable, and we want the derivative of y with respect to x, sorry, if we're treating y as a constant because we want to take the derivative of y with respect to x, this also is going to be 0. So we just have a 1 here and a 0 over there, and then that's going to give us our formula for dz dx. And it's going to be a negative the partial of capital F with respect to x divided by the partial of capital F with respect to z. So similarly, the dz and dy would look like that. So let's see. Let's do this as an example. We got z, e to the z is equal to x times y times z. And let's ask ourselves to find, I might need to do this on another page, find dz dx. Sorry, we're going to do this on another page. All right, so that formula says that we first need to start off by writing this as a function of x and y and z that's equal to 0. So the first step is to bring everything on the other side. It doesn't matter which side we bring it in. I think it might be easier to put the e to the z over to the right side. I don't think it matters, but x, y, z minus e to the z, as long as everything's all on one side. So now I have this function of x and y and z, and that's equal to a constant. So I just need two things to find dz dx. I need to find the partial of f with respect to x. I think that goes in the numerator. I need partial of x with respect to z. That goes in the denominator. So I need to take the derivative of this thing with respect to x. The yz is constant, and then e to the z is constant, so that's all gone. So this is just yz. The partial of f with respect to z is equal to, this is xy, minus e to the z, derivative of e to the z is e to the z. So, what were we doing again? Oh, dz dx. dz dx is negative df dx over df dz. So negative df dx is that first one, that's yz, divided by xy minus e to the z. So I guess that would be it. What does that mean? I don't know. It's just a derivative. Well, if you really want to know what that means, it might be nice if we have a picture of it. So that function in itself, when you say it's not a function, remember it's a relation between x, y, and z, gives us something that may not pass the vertical line test, and vertical with respect to z, you know, going up and down. And clearly, by looking at some of these drawings, some of these parts of the picture, we see that it's not a function. Z is not a function of x and y. But for some reason, whoa, wait a minute. Let's try that again. I wanted to stop it somewhere. But for some reason, if you somehow wanted the derivative somewhere at a particular point, like say you want to find out what happens as you go with respect to x or with respect to y, or even furthermore, if we want to find the tangent plane somewhere at this on the surface, then we will need to use possibly need to use the derivatives of these things. So we would want to use implicit differentiation. So let's say on our graph that we wanted to know what is the slope of a line through the point. And for this, we have to make up a point that satisfies this equation. So I need a point that would satisfy this equation. 1,1e, maybe? I don't know. 1,1e? Would that work? No. E11. E10. No. Oh, geez. I have to try to come up with a point that would make this work. I can't put 0 because that'll make this disappear, and e is never equal to 0. So if I make x equal to e and z equal to 1, will this work? E11? X is equal to e, y is equal to 1, z is equal to 1, and this is e is equal to e, so it will work. Okay. So now I have to try to find that here. Where's E11? E in the x, this is my x because I didn't stop it at the right place. Right-hand rule, this is my x. So I'm going e in x, 1 in y, and 1 in z. So I'm right here. So what I want is that if I want to find the slope going in the x direction at this point, what would that be? So the slope of the line through the point E11 in the x direction is given by the partial of z with respect to x. And then if you notice, the partial of z with respect to x had x and a y and a z in it, right? So we have 3 values to fill. And the x, this is negative yz over xy. So negative yz over xy minus e to the z. So you simply put those values in there. 1, negative 1 on top. This is e minus e. Uh-oh. That's not good. Wow, what can you say at this point? The slope is undefined, so it must be going straight up. Kind of like how I drew this. No. So it must be going straight up and down. So we have an infinite slope, which means this thing is going, line must be vertical. Didn't mean for that to happen, but we got 0 in the denominator, we got an undefined slope, and so we must be talking about a line that goes straight up and down. That's our tangent line at that point. All right? All right, so on Thursday, I'm going to give you guys a quiz on tangent planes. The tangent plane that we studied last week, I think on Thursday last week, right? We did tangent planes last week. 14.4, yeah. And then we'll continue talking about the tangent plane here. We're going to continue talking about the directional derivatives and gradients next time.